doing in chapter 2 in section 2.2. We're going to do limits as x approaches infinity. I like to teach you understand. You guys have done this before. But I want you to think about what it really is. It's end behavior. What's the function doing when you get far away from the origin? We're not doing the sandwich thing. Cross that out. Tomorrow we're going to do limits as x approaches a value. We get vertical asymptotes. And end behavior is kind of embedded in all of this. And I don't know about using substitution by limits that are not obvious. Sometimes I feel this is rare. So first thing we're going to look at is we're going to look at the graph y equals 1 over x. Since I don't have it there, I'm going to count. So y equals 1 over x. And I want to find the limit as x goes to infinity of 1 over x. I also want to find the limit as x goes to negative infinity of 1 over x. These are horizontal asymptotes. And you guys learn something to help you remember it. I don't do that because I'm just too to remember. It's easier just to think about it. And if you need to use your graphing calculator to visualize what we're doing, then you use it. You will be expected to do this without a graphing calculator. And so I'm going to add a page, start all over, and I'm going to graph 1 over x. Now you should know what this function looks like before I even hit enter. This is one of the ones you have to know. It's a rational function. It does not behave nicely at 0, but I'm not asking what it does at 0. I'm asking what happens when x gets really large. I like that. X gets really large. What's happening to the y value? Remember, what's a limit? You can take your mouse and click on X. Right? What's this get close to? 0. What does it go to? No, that's not it. Although it wouldn't hurt us, would it? Got hit. Okay. And I could zoom out on it, by the way, as well. So, the limit as x approaches infinity is this. It's 0. It's the y value. What is the limit of 1 over x when x goes to negative infinity? It's 0. They're not always the same. You want to think they are, but they're not. So one of the equations of the asymptotes is y equal to 0 for both of them. But it's not always going to be the same answer. Okay, that's all we're doing. So if we go back to my slide, what if I have 1 over x to the k right here? You know, what if you have the limit of 1 over x squared as x goes to infinity? I could graph it. Looks just like the other graph. What's this going to? 0. Put numbers in. Try 1 over 100. I'm going to teach this more as not how to do it. And then you get the equation. Be sure you pack it over to the next page. You get this piece right here. The line y equals b is a horizontal asymptote of the graph. So you have to look at the question and answer the question. They ask for what's the limit, you give it 0. They ask for the horizontal asymptote, you give them y equals whatever the y coordinate is. Remember what a limit is. It's just the y value as x gets close to another. We're looking for horizontal asymptote. We're looking for end behavior. So let's go ahead and graph that one. I could do it, and I'll show you a couple ways. I'll show you the formal math way of doing it, and then I'll show you what I call the easy way. And you want to do the easy way. was x divided by. And so use your calculators and look at the pictures if that helps you. X squared plus 1 plus 1? Yeah. Something fun. It's something I don't like about this step. Okay, so then I'm going to want you to think. And there it is. You probably can even tell me right there what the first time I'm doing that. Or doing any word. 1 and negative 1. They're not the same. That does not work. And we could zoom in on it more, but I'm not going to do that. Okay, so it's y equals 1 and y equals negative 1. Is that okay? I'm just looking out the window and I want to see what happens far away from the origin. I'm not interested in what's happening in parking lot. I'm interested in the big clouds of hanging over Minneapolis. And that's what this is. You're looking at n being linear. And unfortunately, sometimes they can give you problems with the graphing calculator because you know what the end behavior is going to be. You don't know how to set your window. Because you might want to look at end behavior, but then also what happens to the origin. And if you have curves that hit the x-axis really close together to 0, I mean, like really close together, like 0.001, and I know you have something like that, then you have to really be able to analyze the graph algebraic. Graphic calculators are wonderful, but sometimes they don't know the source codes. So how do I do this algebraic? Now first I'm going to show you what I call the hard way. I'm going to take the limit as x goes to infinity of x divided by the square root of x squared plus 2. And what I'm going to do is it's a little trick. I'm going to divide by the highest exponent, which is x. And really, what's the square root of x squared? It's also x. So I'm going to divide numerator and denominator by x. Is that okay? Because that's what? 1. Not changing. So when I divide it, I'm going to have the limit as x goes to infinity, and then we're going to have a little complicated algebra. That's easy, that's 1. And then I have to do this. So how do I do the square root of x squared plus 1 divided by x? We have to remember that if we have the square root of a over b, you cannot simplify that. You can't simplify the square root of a over the square root of b, and that's equal to the square root of a divided by b. Remember that? Square roots. No? Okay. So if I have the square root of x squared plus 1 divided by x, I can't divide that. They both have to be under a radical. So what I'm going to do is do a little manipulation. X squared plus 1, and x is the square root of x squared, isn't it? What's the square root of x squared? I'm not going to flip anything. I'm going to do this in a second. This is still the same thing. Let's do one thing at a time. And then I can rewrite it this way. Because really, I'm going to do nothing more than this one moves in arithmetic. So that's what algebra is. Algebra is arithmetic with letters. I'm not. I'm just looking at this piece right now. All I'm focusing on is this division. That's what you're... Sorry. We're just going to do that. We're going to get that fixed in a second. Notice I left it blank. Not blank. I'm just worrying about that one. And you know that you can divide, I have to divide actually, into both of those. Because it's really this. It's really 1 over x squared times x squared plus 1. You must use the distributive process. You can't divide it x squared. That's not very fair. What about 1 over here? 1 plus 1. So now distribute and you end up with 1 plus 1 over x squared. This is what I call it. So that's what I'm going to put in. I bet it's all connected. I'm going to put that right back in up here. There it is. Now, I can write the limit out. I've got the name limit there, and the last name. That's just a lot of writing. Are you okay with just taking the limit of each piece and kind of like the limit of 1 is 1. What's the limit of 1 here? 1. And what's the limit of 1 over x squared? It's 0. Remember we just did that. I don't know where the slide is. 1 over x squared is 0. So, this is 0. So what's the answer? 1. Seems like a lot of work, doesn't it? And no, because it's not 0. It's looking at what happens if x is really large. Zeros have nothing to do with horizontal axis. That's what I'm confused. But let's do it easier way. Because I divided by x, I got this. How did I get this big right here? This to this? Because that's what that means. This is. Then I divided it. And I did this. 1 over x squared times what x squared is. For x, 1 over x squared times x squared is 1. Then distribute. 1 times 1 over x squared is 6. Okay, just algebra. I could have just gone from this line right here to this line and divided, but I must divide into both terms, not at times. The multiplication of fractions and free algebra. And I said, if you've got pluses there, you can't do what I'm doing. It has to be times. But you know what? It's even easier than that. Let's go back here. X is going to be a large number. And it was x over the square root of x squared plus 1. Now, if I had billions and billions of dollars, does the one matter? If you gave me another dollar, would I really care? If I'm poor and I'm counting my pennies, one might matter. So when x gets really large, this looks like this. I'd rather see you understand it this way. When x gets really big, it looks like that, doesn't it? And what is the square root of x squared? It's x. X is a positive number, so it's big. So it's x over x. And what's the limit? We never get there. We never get there. So long as we never get there, we can reduce that. Okay? Yeah. That's, to me, the easy way. Just to think through the problem. That's why I have some extra examples for you. I'm going to go to negative infinity. The correct way is to do the dividing by x, and then it'll take you a while to do it. And I don't think it leads to a better understanding. I think it leads to here's a how-to. Where if you think about what the graph looks like, you can understand it better. Now, I don't know what this graph looks like. I didn't know what it looked like. So I'd have to graph. Now, what if I do negative infinity? It's x over the square root of x squared plus 1. What happens if it's plus 1? Because x is going to be really tiny. It's way over there, but it's like tiny. First off, it will become positive. So this is approximately x over the square root of x squared. This is a positive number. What about that one? It's a negative. So it's looking like x over x. But this is a negative number, and this is a positive number, so let's just divide out 2. X goes to negative infinity. It must be a negative number. That's really all there is. Didn't give you the polynomials. I'm going to add a page. I'm going to steal from the other page. I don't know. This is out of the old textbook. Now, oh wait, I'll get it. No, but it's going to help you with the homework. Read this as home. Consolidate got confused on this kind of stuff. Now we can graph these. This should have an X here. Okay? Look at the first one. Let's make this easy. When X gets really large, what happens to X over X minus 5? Looks like X over X, so this is equal to 1. Now you could do the divided by X and use that theorem. That's mathematically what's happening. And here I would divide by what? T squared. Or, I say, I don't want to do that work. What happens to the 7, Grant? This goes away. Now what you have is, be careful, T squared over negative T squared. And no matter what T is, I don't care if it's X, should have been X. There. Didn't work without that, but if T goes to negative infinity, it doesn't really matter because it's squared. So we can square negative numbers always. So what's this end up being? Negative 1. Let's try this one. It's now, because it's considered roots, remember I told you to do this. You can do the cube root of the limit as X goes to infinity. Get that main limit there. Allows you to do. Then this makes it an easier problem. I think it's easier. So to find my limit, then I'm going to cube root it. So what's going to happen? What about 1 and 4? Are they going to matter? No. And so this is the cube root of, as X goes to infinity, I'm really looking at that. What's that equal to? 8x squared over x squared. 8x squared over x squared. So you need to see it. I'm that way too. That's 8. What's the answer? So it's y. That's the easy way. The hard way is to go under that radical and divide by the x squared. Take the limit of the 1 over x's, and that's hard. Isn't it just easier to say when x gets big, these numbers here, they don't really matter. It's approximately equal to. You're looking for a limiting value. This is a challenge one. You'll probably have to use your graphic calculator to do that one. I'll put it back, but let's go back to some of these other ones. What about this one? The limit, now we've got to worry about two things here. We have the limit as x goes to infinity of sine of x over x, it should be on your and the limit as x goes to negative, not a negative, I could do that one, goes to 0 of sine of x over x. So you have to read carefully at the problem, because we know this one. What's that one? 1. That's different. So don't fall in the trap of just saying, oh, I see sine of x over x, the answer's 1, because it depends on what x is doing. So now, if you think about this, what's true about the sine of x? We're not going to use the squeeze theorem. In a way, we are. It's trapped between what? Negative 1 and 1. So x gets big. It's just oscillating. So all the time we're going to do, the denominator is not doing that. The denominator is being huge. So pretend that you're at the maximum value of sine of x, which would be 1. And you let the denominator go 10 to the 10. What's that getting close to? No. Is there any work to show? Not much. Not much if you want to do it what I call the easy way. How about this one? I'm going to let you in when you probably should. But they asked me lots of questions on this. And then once they got it, they were really happy. So what are we going to do with this one? This is the same problem. In terms of the plus, you break it into two fractions. It's 5x divided by the x plus sine of x divided by the x. You know, if I add 2/3 plus 5/3, that's the same as 2 plus 5 over 3. Just think of going backwards. Adding fractions, remember those guys? The denominators are the same, you just add the difference. This is is the same thing. Look at this one. They have the same denominators. What would you do with the numerator? You would add them. So these are the same thing. And I can divide that. Well, part of it I can divide. Now, the main limit there says I can take the limit of the first fraction plus the limit of the second fraction. So I'm going to write that, but I usually just do the problem to tell you what the answer is. And so it's going to be 5x over x plus the limit x goes to x of the sine of x over x. I just did that one. How big was that one? 0. I like that. So this one's 0. And what's this one? The x's cancel out, not 1, but 5. Now what's it? Because you can cancel the x. Sure, you find the x to be 1. Just like, it would be like you saying, let's just divide the 3 into the 2 and not the 5. That's not true. Always go back to real things that you know about. So we will do 29 on this little worksheet together. We're going to graph it. Because what's the underlying concept? The underlying concept is what's the end behavior. Now, this is so little. I think it says positive, but am I right? Now, I could graph this on my graphing calculator. Yeah. Or I could just graph it. Now, I would expect that you know what this looks like. What's the y-intercept? 6. Oh, you're doing the first one. No, this one's 11, right? And what is the slope cut? You go over 1, down 2. So as x approaches infinity, what is my function going towards? You could substitute it in, and you could put in even 100, and so it looks like it's going to negative 200. Plus that 11, but it actually gets smaller and smaller, doesn't it? And bigger and bigger. The 11 just equals 6. So it's negative infinity. But pretty much it's just answer only. Yeah, ask questions. No, actually there's no horizontal asymptote. We're actually only finding limits. If they ask for the horizontal asymptote, then you'd say there is none. Or if there's one, you'd say y equals whatever it is. Yes. Yes. Let's look at the next one. I'm going to use my knowledge from pre-calculus to do this. Now this is negative infinity. I'm probably going to see those. Say what? And be careful that you read the problems carefully. Because sometimes they throw in the highest degree at the end. Now do you remember what a degree is? In a polynomial. The highest what? Exponent. It's a polynomial. Now, forget all that other junk. Just look at 3x to the 4th. Does anybody remember what x to the 4th looks like? Well, x squared looks like this. What's x cubed do? And x to the 4th comes back. Guess what x to the 5th does? No, because you're talking odd, even. Well, this isn't either. So all I'm going to do is look at that piece. And so I know that x to the 4th looks like some sort of w. What's the end behavior? It's over here. Oh, no, it's negative infinity. It's still the same answer. What's the end behavior? Infinity. Is there anything to do? No. You can graph it. You're looking at what is the range. We're talking about the range. Is there a constant there, or does it go off to infinity? Not something like this. You should know what x to the 4th does. Yeah. You just ignore all of these other. When it gets really, really, really big, like our dad, those are better. All right. You guys inherited, unfortunately. But they become negligible, yes. There's nothing more. There aren't any. No, they're pretty direct. Some get a little tricky. Be careful with 36, because you have to read that whole numerator or fall in the trap that I fell into. Infinity. Yeah. What if you had a limit, just do one more, and it's 2x cubed minus 5x, and it's negative 8x cubed plus 2x, as x goes to infinity. Now, remember, we don't care about what happens away from the leading terms. Those are the leading terms. They're not always in front. These are negligible. So what does this look like? It looks like 2x cubed over negative 8x cubed. What happens to x cubed? They cancel out. So what's the answer? Negative 1/4. Or negative 2 over 8. It's perfectly acceptable. Do you remember there was a theorem? If they're polynomials, you have limit x goes to infinity or negative infinity, ax to the x plus over bx to the x. These exponents match. This ends up being what? Remember this from last year? A over b. Maybe that's what you were thinking. What if I have the limit, I'll just do this, as x goes to infinity, and it's ax to the n plus 1 over bx to the n. So that this exponent is bigger than the bottom exponent. What's that do? This is properties of exponent. What is x to the n plus 1? It's equal to x to the n times x. And that's going to be over x to the n. What's going to happen to x to the n? But just think about it numerically. This exponent is bigger than the bottom exponent. So this is going to go on this x, or x squared ratio. It's going to go to infinity. What's the last one? The limit as x goes to infinity of ax to the n. And let's make the denominator exponent bigger than the numerator exponent. What's that going to do? It's going to go to 0, because it's going to look like 1 over x. So an a and b. But those are irrelevant. And that's all that will happen when you do polynomials. Notice we have roots. Roots you're going to have to think a little bit. So like if it's the square root of x squared plus something, doesn't matter, because that's going to look like just a plain old x. Okay? Is that okay? The big thing is, I just look at numbers. We're looking at end behavior. And if you need to also graph these so that you start feeling more comfortable, keep so. But you'll eventually have to be able to without a calculator. 32. And sometimes they don't have the leading coefficient. It's not in front. So maybe you want to put it in front. I prefer to write my polynomials with the highest power first. Good, Chris. Does this look a little easier now? What happens to the 7 and the 1? They're going to go away. So this looks like negative 3x cubed over 2x cubed. And since these are the same degree, it's going to be what? Negative 3 halves. If they ask for the horizontal asymptote, you would write y equals negative 3 halves. Does it matter that we're to negative infinity or positive? In this case, no, because these are identical. So when you finish that worksheet, go back to the beige worksheet on the back side, and now everything on there except for the very last problem. And the first problem on there, and I don't know where mine went, the first problem on there is 2008 multiple choice. And it's a problem that they actually probably worked true out of the exam because so many people got it wrong. You must look at, we're all asking the x going to positive infinity and x going to negative infinity. And they're not always the same. This case is the same. This is a negative infinity here. Right? When I put on my calculator, I just know that it's going to go down to negative 3 half. I don't know what happens at the origin. No idea. But if x goes to negative infinity, it's going like this, and positive things going there, and it could be doing all sorts of stuff there. I don't know. Limit's not negative infinity. What's the limit? The x is going to negative infinity. The y value is getting close to negative 3 half. Let's see if I can remember this long enough to do it. So I got it. Oops. Well, let's graph it. Let's always remember what my graphs were. Good and bad. I must use parentheses, or I will not get it right. So these, if you understand what's going on, are very fast. Then you need to focus on 2.1, and you should do that beige worksheet. And I'm always paying the whoops. There it is. So I don't know what's happening in here. Here I probably have to zoom in a little bit to see what's happening there. But you can see it's negative 3 halves on the right, negative 3 halves on the left. Remember, we're looking for the y coordinate. Limits are y values. Are there questions on any of the 2-1 book problems? I've done all the other ones. If you haven't done them, you might want to do them. And then I make a picture. There it is. I didn't zoom out on it. I can zoom out. That won't be a picture. Look at that. Sure looks like a horizontal axis up there. Right. Yeah. Oh, yeah. Number 37. That's what I was concerned with. Okay. This worksheet here. You could do all of these now. You especially should try number 9, because that's the one that was on the 2008 exam that they threw out. And they actually wrote a note there saying teachers need to teach this. So make sure they get this. Oh, I'm looking at the wrong section. Okay. I did this one, but we'll do it again. This is 2.1. 37. Maybe I didn't do this exact one. I did a picture like. And this is what you have to know in your quiz. Yeah, we might have a picture. Okay, which parts? F and G. These are the true-false questions. I prefer that we just answer the question. When you do true-false questions, for it to be true, it must always be true. Am I doing the right one? No. If you understand what a limit is, then you shouldn't do that. Well, they are. I hope I got the right ones. Okay, let's do F. What's the limit of my function? What's the y value when x gets close to 0? Let's put a point. Let's put a point here. I'm going to drag this down from the right side. Remember, you must always look at it from the right side. Okay. What's this? Going to 0. What's it coming from the other side? So I don't know what the answer was. What is f of 0, though? 1. So when we get started on continuity on Thursday, we're going to talk about that. This is definitely not a continuous graph. What is the limit as x approaches 1? I'm going to put my dot here and drag it. You must always check for both sides. From the left, it's 1. I'll just write this way to save time. And from the right, my dot down here, and I'm going to drag it over there, it's 0. It does not exist because the limit from the left, you're going to have to get the because left does not equal the limit from the right. G. I would just ignore the true false part and just ignore all the numbers they give you and just do the props that you check. So I know they gave me a number for that one. They gave me 1, which isn't true. And F is true. I don't like it with the true false. And you'll have problems just like this on the exam. It's just as easy as this. They'll say, what's the limit of this? Of course, some people are going to say 1. What is the value of the function? Getting close to. But not when you're there, but when you're really close to being at 0, what is that value of the function? I don't care what happens. That's unimportant. And yeah, you'll see questions like that. And then they have multiple choice, but I have them up on Blackboard. I haven't migrated over to them. I'm far from it. Other questions? And then make sure you do the back side of this. Because tomorrow you're going to have a worksheet and you're going to have some book problems. So tomorrow's time's a little bit longer. And I still have to teach you. You just can't do number 3. Well, you can if you think about it, but it's hard. Make sure you read what x is approaching means. Yes. 66? I hope so. Now, on these true-false questions, or on any of the multiple choice questions, a lot of you like to just write A, B, C, D, or just true-false. That is not okay. So you need to actually show me the work. And this is the limit. And I thank you for asking questions, because if you don't ask questions, I don't really know. Let's see what I'm thinking. It's x plus sine x. And this is the class we use for algebra. It's a true-false question and justify your response. So first I'm going to rewrite it. This is the limit as x goes to 0 of x over x plus sine of x over x. Is that okay? Just add a fraction. Now take the limit separately. Now I would just answer the question, but if you really want to show your work properly, really do this. What's this? Remember, I don't care what happens at 0. You're right, it's not defined at 0. It's what? 1. Because as long as I'm not at 0, I may reduce that. And what's this limit? We know this one. 1. So the answer is 2, and it's true. There's my work. If you don't want to write this line, I'm okay with it. So if you really want a nice proof, you need that. In fact, 75 is actually proving, I think, yeah, is actually proving that the limit as theta goes to 0 of the sine of theta over theta. Are you okay with other ones? We didn't do the sandwich things. You can skip those if I sign them. They're not that bad, but you need to be able to do a problem like 37, 38, 39 through 44, finding all those limits. I think. And then being able to do something like the limit worksheet. And what about problems like 19 through 28? Any of those? What about 22? There's no radicals in there, but you still have to know the radical spectrum. Okay, say number 34 on this little worksheet because it'll say it's a little time tomorrow. And I won't have to answer the questions. Now you got to think a little bit when you're zooming out on this. So what is it going to matter? The 30 and the 5. So this is going to look like 2x over 6x to the 12. If we can reduce or not, I don't really care about the 2 to 6 because they're irrelevant. That's 2 6. And if I reduce this, that's 1 over x to the 11. As x gets really big, what happens? 2 6 doesn't matter either. It's 1 divided by a huge number, so it's going to 0. Notice I don't look at the other terms because they just don't tell me anything. Yep. And this is my work. I just have the answers. And there's no word. Because what's 1 divided by a huge number? Put in 100. 1 over 100 to the 11th power will probably give you an overflow where your calculator works. Just think of having this many people in the world, and you're going to take $1 or 1 loaf of bread and give it to all of them. Everybody gets nothing. They wouldn't even get a grain. Yeah. This is another one of those radical ones. The limit as x goes to negative infinity, and again, we're just going to think through the problem. Now, the ones with the radicals can be troublesome. You have to read carefully what's under the radical. I have an x squared and I have an x. So this is really looking like a square root of 3x squared over x squared. Because when x gets really small, even though that's still changing as well, okay, Britt? These don't matter. Only look at the leading term, the highest exponent, and it's an x squared, sorry. And that looks like approximately the square root of 3, actually equal to, over, and this is what square root x squared is x. And then I have an x squared here. So that looks like the square root of 3 over x, right? You have to be careful with the signs. Check the signs in a second. So if x goes to positive infinity, well, I don't see the matter. This is going to what? 0. Even if it goes to negative infinity. If it goes to negative infinity, it's going to 0, but actually it's still going 0 from above the axis. Because what's true on this numerator? It's always what? It's always, it might be greater than 1, but it's always positive, right? And what's true with the denominator after bigger than 1? It's always positive. You square any negative number, it's positive. The only time that x squared is smaller than that is when x is a fraction. That's number theory. Number thinking. More questions? Is this up online? You said no so fast. I don't know. Did you get yours? Or is that mine? Oh, okay. You got yours. Okay. Oh, the charts? No. You can plug it in the wall, you can plug it in. I think you can plug it in. Oh, because if you want to change the files around. You want to get the software, and that's how you do updates and stuff like that. But it's a matter of, I'll show you.